When you pull up a web page, you see text, you see pictures. Simple, right? But what does a computer actually see? Well, today we're going to peel back the curtain on a digital document and look at the hidden world of code, structure, and metadata that actually makes the whole thing tick. So let's dive in. Really think about it for a sec. A web page loads and instantly your brain just gets it. You know exactly what you're looking at. It's this familiar landscape of headlines, paragraphs, links, the whole deal. It's totally intuitive for us. But for a computer, that's just the finished product. That's the house after it's been built. Before any of that can even show up on your screen, the computer has to read the architect's blueprint. And in the tech world, specifically in information retrieval, we call this whole package a document. But a document isn't just the text, not by a long shot. It's really four things all rolled into one. The words themselves, yeah, but also the structure holding them together, the style that makes it all look good, and crucially, the semantics, the meaning behind it all. Okay, so how on earth does a computer read that blueprint? Well, it all starts with the absolute foundation of the web, something we call a markup language. You can think of it like the hidden scaffolding that's holding up every single web page you've ever visited. What markup does is add these invisible instructions to plain old text. And here's the key part. It doesn't say, hey, make this text big and bold. Nope. All it says is, this text is a heading. That's it. The browser handles the rest. And this idea, this separation of structure from style, it's honestly one of the most important concepts that makes the web work the way it does. And what's really cool is how these languages are all related. It's like a family tree. At the very top, you've got HTML. Think of it as the grandparent, the one who wrote the rulebook for everyone else. Then you have HTML, probably the most famous one. It's the web's workhorse, a direct descendant of HTML made specifically for web content. And then there's XML, kind of like the flexible cousin. It lets you create your own custom tags, which makes it super powerful for organizing all sorts of data. All right, let's make this real. Take a look at this simple mind of HTML code. See those H1 tags on either side of the words HTML example? That's the markup. And notice, it's not saying anything about fonts or colors. All it's doing is defining that piece of text as a heading level 1. And boom, this is what your browser turns it into. It sees that H1 tag and knows exactly what to do. Display a big, bold heading. So what's the big takeaway here? It's simple. The markup provided the structure, and the browser provided the style. Okay, so that's the blueprint. Let's peel back another layer, shall we? If markup is the blueprint for the house, then every document also carries around a kind of digital ID card. And we call this metadata. Metadata is pretty much exactly what it sounds like. It's data about the data. It's all the information that isn't part of the main content but describes it. Things like, who the author is, when it was published, even what language it's written in. And this stuff basically comes in two main flavors. First up, you have descriptive metadata. The best way to think about this is like the label on a file folder, right? It tells you who wrote it and when. Then you've got semantic metadata, and that's all about what's inside the folder. It's the stuff that tells a computer, hey, this document is about astronomy, or this is about financial markets. It gives the machine some much-needed context. So, now we've got our blueprint and our ID card, but how does something like a search engine actually read the millions upon millions of words inside these documents? It can't just scan the page like we do. It needs a system, a process. And that system is called document preprocessing. Think of it as a 5-step program for teaching a machine how to read. First, it chops up the stream of text into individual words. Then, to cut down on the noise, it just tosses out all the common useless stop words, words like the, and is. Next up is stemming, which is super clever. It boils words down to their root form, so running and ran just become run. After that, it picks out the most important keywords, and finally, it starts grouping related ideas together with a thesaurus. And just like that, the text is ready for a search. And you really can't underestimate how powerful this whole process is. Just take that one step, getting rid of stop words. Doing that alone can shrink a massive search index by 40%, sometimes even more. That is a huge boost for speed and efficiency. It's literally the reason a search engine can spit back results in a split second, instead of making you wait for minutes. Let's zoom in on stemming for a second. This process is so important. It's what allows a search engine to be smart enough to know that when you type in connect, you're probably also interested in pages that talk about connection or connecting.
It's brilliant, really. It groups all the different variations of a word under one single conceptual umbrella.
Okay, so we've pre-processed everything, but we're still left with an absolute mounting of data from billions and billions of documents. So the final challenge is, where do you put it all? How can you possibly store it efficiently? Well, that's where the magic of text compression comes into play.
And there are basically two main approaches to this. You've got statistical methods, which are a lot like Morse code. They just assign shorter codes to the letters or words that pop up most often, like E or the. Then you have dictionary methods, which work differently. They'll spot a long, repeating phrase, something like the United States of America, stick it in a dictionary just once, and then every other time it appears, they just use a tiny little pointer back to that entry. Super efficient.
And the results? They are absolutely stunning. A state-of-the-art compressor can take a huge collection of text and shrink it down to less than a third of its original size. And this isn't just about saving hard drive space, right? This is the technology that makes things like streaming video and instant search results even possible. But as this chart shows, it's always a game of trade-offs. Take a look at Huffman coding. It's pretty fast, and you can even search the compressed data. Now compare that to BW2, which is what BizZip2 uses. The compression is great, but man, is it slow to decompress, and you can forget about searching it directly. So there's no single best method here. It all comes down to what you need most: speed, size, or searchability. So from markup and metadata all the way to stemming and compression, we've really seen the incredible journey a document takes just to be understood by a machine. At the end of the day, all these steps are about one thing: helping computers process our words. But the huge question, the one we're all looking at for the future, is this: can they ever move beyond just processing words to actually understanding our meaning? With the semantic web evolving every day, that's the next great frontier. And that is a pretty fascinating thought to leave you with.